Welcome to the Explainer. Today, we're diving straight into a massive paradox in the world of machine learning. It's a mathematical illusion, and it's one that affects everything from whether your credit card gets declined at the grocery store to how a doctor might diagnose a life-threatening illness.
I mean, it sounds totally impossible, right? If an AI model is 99% accurate, how in the world could it still be completely useless? Well, to understand why a 99% accuracy score can actually be a complete and total failure, we first need to look at how machines actually learn.
Okay, Section 1. Understanding supervised machine learning. Let's just quickly lay the groundwork for how these predictive models operate, since this is the bedrock for so much of the AI we interact with today. As you probably know, in supervised learning, data scientists aren't just throwing raw data at a computer and crossing their fingers. They use ground truth, basically explicitly verified labeled datasets used to actively teach the algorithms. It's literally like giving the computer an answer key on a math test. By studying the inputs alongside the correct outputs, the model learns the underlying patterns so it can eventually make predictions on brand new, unseen data in the real world. Which brings us to Section 2. Classification versus regression. Within the supervised learning space, there are two primary ways an algorithm can make its predictions, and they tackle very different kinds of problems. On one hand, you've got regression. That's all about continuous numbers. Think estimating an upcoming house price based on square footage or predicting tomorrow's exact temperature. The model is fitting a line or curve to find a numerical value. But on the flip side, we have classification. This isn't about continuous numbers at all. It's about drawing a hard decision boundary to separate data into specific categories. Looking at an email and deciding, is this spam or not spam? And that leads us right into Section 3 and a huge real-world hurdle, the imbalanced data trap. Classification is incredibly powerful for sure, but it has a major blind spot.
Picture this. We're building an algorithm to catch credit card fraud. We train it on 90,000 perfectly normal transactions and just a tiny, tiny slice of only 400 fraudulent ones. Now, that is totally realistic. Fraud is relatively rare compared to normal shopping, thankfully. But look at how wildly skewed that ratio is.
Here's the kicker. If a lazy, poorly designed model just defaults to guessing normal for literally every single transaction it ever sees without even analyzing the data, it hits over 99% accuracy. But it completely fails 100% of the time at its actual job of catching fraud. The metric looks absolutely fantastic, but the model itself is utterly useless.
And boom, the illusion of accuracy is shattered. To escape this metric trap, data scientists have to dig way deeper. They pull up a confusion matrix to see exactly what kind of mistakes the model is making. They look at precision, meaning of everything flagged as fraud, what actually was. And recall, how much of the real fraud out there did it actually manage to catch? They even smash these together into a weighted average called the F1 score, or use AUROC to see how well the model ranks predictions. The point is, accuracy alone, it's just not going to cut it anymore.
All right, Section 4, fixing imbalanced datasets. Properly evaluating the model is only half the battle here. If the data itself is broken, the model will struggle, so we have to actively fix the scales before the learning even begins. So how do developers fix it? Resampling techniques. One way is undersampling. You just randomly delete data from the massive majority class, like dumping tens of thousands of those normal credit card transactions until the numbers match the fraud cases. The catch? You're throwing away potentially great information. The flip side is oversampling, where you simply duplicate the minority data over and over. But the massive drawback there is that it increases the likelihood of overfitting. The model just memorizes the duplicates instead of actually learning true patterns. To dodge both of those drawbacks, data scientists use this brilliant technique called SMOTE, synthetic minority oversampling technique. Instead of just deleting data or blindly copy-pasting it, SMOTE actually generates brand new synthetic data points for the minority class. It picks a point, mathematically finds its closest neighbors, and literally draws a line between them to create a completely new synthetic point along that path. You get a perfectly balanced dataset, zero lost info, and no lazy duplicates. Now for Section 5, AI in cancer detection. Let's really raise the stakes here. We've talked about credit cards, but let's see how these exact classification and data balancing techniques are deployed in a literal life or death scenario. Look, we all know there's no cure for cancer right now, so detecting whether a microscopic tumor is benign or malignant in its absolute earliest stages is everything. Spotting it in stage 1 or 2 can literally be the difference between life and death. The problem is, manual clinical diagnosis takes a lot of time. And let's be real, the human eye can miss incredibly subtle microscopic patterns. This is exactly where supervised learning steps into the clinic. Developers take raw hospital datasets, like microscopic histology slides, pass them through a pre-processing stage to clean up the noise, and extract the key visual features. Then they feed those mathematical features into an AI model that's specifically designed to classify the cells as benign or malignant, whether they're looking at breast, colorectum, or head and neck cancers. And the classifiers doing the heavy lifting here are seriously advanced. Researchers are utilizing models like support vector machines, random forests, and deep learning architectures like convolutional neural networks, or CNNs. In fact, in recent studies, using models like light GBM and CNNs on these carefully processed medical images has achieved well over 99% accuracy in recognizing the microscopic patterns of cancer that humans might completely miss. But wait, remember our imbalanced data trap? Medical datasets are notoriously skewed. You almost always have way more healthy patients than sick ones in a dataset. If they aren't extremely careful, the AI just guesses healthy and looks like a genius. That's why researchers heavily rely on those oversampling tools we just talked about, like SMOTE. Recent studies on head and neck cancer specifically proved that using techniques like SMOTE actively boosted the model's ability to accurately predict patient survival. Why? Because it forced the AI to truly learn the minority class, the actual cancer cases, instead of just ignoring them. Is an absolutely incredible blend of data science and medicine. But it leaves us with a pretty profound final thought. As data scientists completely master these datasets, conquer the imbalanced data trap, and build algorithms that consistently and legitimately break that 99% accuracy barrier in early cancer detection, how heavily are we going to rely on them? In the near future, how fully will you entrust your own medical diagnosis and your actual future to an AI's mathematically drawn decision boundary? It is definitely something fascinating to consider. Thanks so much for joining me for this explainer, and as always, keep questioning the data.